Hello, welcome to this lecture number 2 of week 3 of this course Radio Astronomy. We will continue discussing on the antenna theory. Just to give you a brief overview of what happened in the last class. We started on antenna. We basically emphasized on the fact that antenna is a very integral part of a radio telescope, and radio telescope is the one of the most important, if not the important component of the entire receiving system of the radio astronomy. So there are state-of-the-art low noise receivers, but antennas also, the design, the engineering marvels the antenna stands for is absolutely wonderful. We showed a couple of different kind of antennas: the wire antenna, the aperture antennas, and patch antennas. Before we continue on several different antennas and other definitions, properties of antenna, we started discussing about the most idealized Hertz dipole and how to evaluate the electric and magnetic field as a function of different distance from the antenna radiating. And we see there are three distinct regions. First is a very near reactive zone, and then an intermediate zone, and or a near field radiating zone, and a far field radiating zone. And we defined them, and that was kind of where we stopped in the last class. This we continue exactly where we left. So this is the Hertz dipole on the top right corner of the same one. L total length of the dipole is L. Half of it is above the XY plane and half of it is below. So the origin is exactly at the near the half midpoint of the dipole. The current flowing is along the Z direction. It's I naught is a constant, and we calculate the electric and magnetic field at a distance r from there. We saw very soon that there is a spherical symmetry in this system, so we converted the XYZ coordinates into r, theta and phi, the spherical coordinates. We figured out that the radial and the theta component of the magnetic field is equal to 0. Only the azimuthal component survives in this case. For electric field, the azimuthal component goes to 0 and the radial and theta component survives. So that's the thing. And we also derived a couple of other important notions, like at large R, the second term in the ER, radial component, goes to 0, because as R tends to infinity, this is R cube, 1 over R cube, so this goes to 0. For the E theta components, the second and the third term are 1 over R square, 1 over R cube, so they goes to 0 because there's one R, another extra R is over here, and so this second term becomes 1 over R square, the third term becomes 1 over R cube, and they goes to 0. Similarly, so only term survives the first term for both ER and E theta. But even the ER, the first term is also R square, that also tends to 0, so ER fully vanishes. E theta, only the first component, which is 1 over R, that exists. And for H phi, the first term, which is 1 over R, that survives. The second term also goes to 0 as R tends to infinity. Now, that's where we stopped essentially last time. And then we defined like several different regimes of R, where KR is less than 1, greater than 1, and much greater than 1. Okay, so now we proceed. The very next step we learn from the electromagnetics is we have E and each H field, so we compute the pointing vector, and that finally turns out, so we have a WR and W theta component, and from there we can easily figure out what is the P, the complex power radiated. We figure it out, and then finally, after integrating total power, comes out of theta and phi. Theta goes to 0 to 2, sorry, theta goes to 0 to pi, and phi goes to 0 to 2 pi, and so the final expression of radiated power comes out to be this, which still has a 1 over r cube dependency. So that's the radiated power, half of E cross H dot ds, and that comes out to be having a real and imaginary part. So yeah, so the P radiated is the real component, and the imaginary component is represented by P, E and H, which is time average imaginary power radiated radially outward. So as so finally the P radiated one is given by the eta times pi L square over 3 lambda square into I naught square. Okay, so as the R is tends to larger and larger, this value is you can see it's 1 over R cube. So the effect of this in the far field radiation pattern is almost 0. Okay, whereas the effect of the P radiation is kind of it remains. So in the near field where R is less than 1, this reactive component of P, E and H still remains, but as R tends to infinity, grows larger. For the far field, this P radiation component dominates, and the other one almost negligibly equal to 0. So for far field pattern, we can concentrate only on the P rad term, which is equal to this half I naught square R radiation resistance, where R is given by 80 pi square L over lambda whole square. Okay, so we go back again and revisit this entire calculation once more. We had from the I which is running in the along the z-axis, we calculated the vector potential. From vector potential we got the H by following Maxwell's equation, and from H we derived E. Okay, and so this is the components of E and H. We replaced the X, Y, Z components with R, theta and phi components. We got only one component of H field is there, whereas two of the E fields are there. Then we compute the pointing vector. From there we compute the total radiated power, and then finally we end up having this expression of power in terms of both real and imaginary component. We investigate the imaginary component and see it is 1 over R cube. So at the far field this component almost goes to 0. In the near field, of course, it remains effective. That's why it's a reactive near field. For the far field component, it only P rad survives, so we express that in terms of I naught and radiation resistance, where radiation resistance is given by this formula. Now let us look at the the radiated power in the far field. Okay, and that if you plot it, it basically will show a structure like the donut. Now remember, this is the radiation pattern in a free space, which is a tremendously idealistic situation. Okay, in a real case, we will show you the patterns. It is not that symmetric, and there will be something called the main lobe and the side lobes which will start appearing, because there will be some kind of a reflection from a nearby what we call ground. So whether the antenna is on top of, just mounted on the ground will reflect. It can be mounted on top of other things, they will also reflect. So this reflection causes creation of side lobes, and if you see, but it is not present in this particular idealized radiation pattern, because this is assumed to be in free space. Okay, so half wave dipole is just like a length of lambda by 2. The concept is there, we already have gone through it, and I0 is there. So we will come and visit again Hertz dipole later on in this week when we talk about other different wired antennas. So we saw the radiation pattern. We showed that some general steps how it appears. So we got the W radiation in terms of R, theta and phi. So W is not just but the real component of the Poynting vector of real of E cross H, and so we can write the, since we know the E theta and E phi, H theta and H phi components can be written in terms of that. So the W rad can be written in terms of E theta square plus E phi square, and so and so. But in case of Hertz dipole, we know that E phi does not exist, so we can write it in form of that. For any other dipole, any other antenna, sorry, these are terms which will basically survive. Okay, so from there we can write U, which is kind of R square W rad, and then from there we also determine P of radiation, which is W rad integrated over the entire theta and phi. That's what we did for the Hertz dipole. And then finally, yeah, so the directivity is basically U theta phi in any direction over the U naught. Okay, and or you can find out 4 pi U theta phi, which is given by this expression on top, over P radiation is defined as the directivity in theta and phi. Directivity is basically how much it is boosted in a particular direction, radiation, in compared to an isotropic distribution. So this will come later on as well. I'm just mentioning it here for completeness. For normalized amplitude pattern, we use the Pn theta phi, which is the normalized radiation pattern, is U theta phi in any direction over the U max, which is the maximum in the bore side direction or the central portion. And the input, the radiation and input resistances are also written in this format in terms of P rad and I0 square. And finally, the effective area is also determined by lambda square over 4 pi times D naught. Okay, this we will again come back. D naught is nothing but the D maximum, which is given over here. This is just to capture the entire picture at once. We will keep coming to this gallery again and again as we proceed. Okay, so as we understood, there was a couple of these terms which came in as we're discussing the radiation pattern. The radiation pattern is an important terminology. Radiation power density, beam width, radiation intensity, effective area, antenna equivalent area, antenna vector effective length, bandwidth, directivity, beam efficiency, antenna radiation efficiency, input impedance, antenna efficiency, HPBW or FWHM, sorry, are basically half power beam width or full width half maxima, gain and realized gain, and polarization. These are very important parameters to understand, characterize a particular antenna, its performance, its radiation pattern, its gain in a particular direction. Supposedly, sometimes we need an antenna to radiate equally in all directions, isotropic radiation. That antenna design will be different from when I need absolutely high gain only towards a particular direction along line of sight. The usage are various. For example, I know that there has to be a downlink setup from a satellite in a particular direction. So we will design an antenna which has a maximum gain or maximum sensitivity towards that direction. In contrary, we would like to radiate in all possible direction, collect information about various communication over the almost horizontally, and for that I need an isotropic radiator. So the design of these two antennas are quite different from each other. Hence, these terms are important, which are used for characterizing the antenna. So antenna design essentially depends on all these terms. Okay, so we will see them as we progress. By this time you have already seen the radiation pattern. We have discussed the ideal radiation pattern in free space from a Hertz dipole. It looks like a donut, but as I said, that's not how the real things look like. And so there we have major lobe, primary lobe, and minor lobes or side lobes. The field pattern typically represents a plot of the magnitude of the electric or magnetic field as a function of the angular coordinates, angular space. Power pattern represents a plot of the square of the magnitude of electric or magnetic field as a function of the angular space. They're both in linear units, the field pattern and power pattern. The power pattern can also be expressed in logarithmic scales, in dB, in decibel scales. Okay, that's mostly what we have. So here are the three different plots. The first one is the electric or magnetic field pattern. You can see the main lobe is in the center, the most prominent one, and the smaller ones are called side lobes, and exactly the opposite one to the main lobe is called the back lobe. Okay, and this arises because that in reality there's nothing called free space. No matter where you place your antenna, there will be some reflecting body nearby. Supposedly I put an antenna on the ground. The ground itself acts as a reflector and it produces these side lobes. Okay, so that is the case. On the second plot, we are showing the power pattern in the linear scale, and it is really difficult to see as compared to the main lobe, it is very difficult to see the contributions from the side lobe and the back lobe. So it is desirable to plot this in a different way, in a logarithmic scales, so that all the contribution of the back lobe and the side lobes and the respective nulls are very prominently visible. Okay, so we also plot this in a dB scale, where now you see the main lobe is there, but also the back lobe, which was almost invisible in the linear scale, now becomes very prominent. Okay, in the power pattern, and the other ones are called side lobes or minor lobes. Now, if I want to create an antenna which is highly directive, then this main lobe has to be the major portion of the entire power, where the power is concentrated on. Okay, all the side lobes has to be extremely minimized with respect to them. Okay, that's the design study. Okay, to find the points where the pattern achieves its half power or -3 dB points is where, so basically what is the half power beamwidth? I go from the central portion where the power is maximum to where the power is half of its maximum value on both these directions, and those are the two half power points. So the angular distance between these two half power points is called half power beam width, or HPBW. Similarly, in the dB scale, those half in power goes to -3 dB in each side from the maximum, and there it comes calculate the entire half power beam width. This HPBW is actually a very important term when we come to defining our field of view of a particular antenna, because these radiation patterns actually are pasted on the sky, and they are the major portion through which the sky is observed. Because as we go away from this 0.5 portion, the power really reduces a lot. That means power reduces in the transmit mode. That means in the receiving mode, the sensitivity of the antenna outside these half power beam width positions are very minimal. Okay, the efficiency goes down. We already have very faint signals coming from the sky. If they are further reduced because of the inefficiency of the antenna, that is not desirable. So we try to concentrate on the region where the antenna is most sensitive. Okay, an antenna is most sensitive within this HPBW region. Of course, we have sensitivity towards this first null. We will come to this little bit later, but the efficiency becomes much lower. Okay, so that's one thing to remember, and this HPBW actually forms our field of view for a particular antenna. So for the radiation pattern, this is again shown in this top right picture. Actually, it has a spherical symmetry, so if you rotate this structure, you will see the entire 3D view. Unfortunately, this is not present here. So you can see the main lobe, the major lobe, the side lobes, the back lobe, etc., etc. Now, for our benefit and try to understand it, we take a slice. Okay, and if you take a slice, you can see these structures placed in the theta axis, and you can essentially be able to understand each of these features. So what is this? The main lobe, the maximum power radiation point at the center, and it goes in either side of this axis from 0 to pi/2 to pi. So near the pi portion, the back lobe maximum happens, and in the 0 point, the front lobe or the main lobe maxima happens. Apart from that, there are a few other components like the half power beam width, the position where in each side of the main lobe the power comes to the half of the maximum power radiated, and the distance, angular distance between the both of them is equal to the half power beam width. When the power goes down to 0 completely, it's called null. First null, because it goes to 0 multiple times. So this is the first null, then second, then third, then fourth, and henceforth. So the distance between these two first nulls is called first null beam width, or FNBW. Okay, then comes the first side lobe, then second, then third, and etc., etc. So these are called also minor lobes, and finally reach to the back lobe. So this half power beam width is very important, as we just discussed, and yeah, so that's mostly what we have to discuss in this particular slide. Now come to the next slide. We have mainly 3 different categories of antennas based on the radiation pattern. First is the isotropic antenna, which is, we have shown the dipole, Hertz dipole in a vacuum or a free space. It's a hypothetical lossless antenna having equal radiation in all directions. In other words, an ideal antenna which can radiate in all directions in a perfect spherical pattern. The second one is omnidirectional antenna, an antenna having essentially non-directional pattern in one plane and a directional pattern in any orthogonal. For example, a dipole antenna has equal radiation in azimuthal plane, whereas directional pattern along the elevation. A directional antenna, all non-isotropic antenna is directional antenna. Okay. The electromagnetic wave can be polarized or non-polarized, so that it is also true for the antenna. That means an antenna can radiate polarized waves. So an electromagnetic wave is polarized. So does the different antenna design can induce polarization in the wave which is radiated out. Okay. To understand the polarized antenna performance, E and H field pattern has to be studied. This is also termed as principal E and H plane patterns. Okay. So we sometimes we also need to look at the difference between the E field and the E plane and the H plane radiated power to understand the polarization characteristics of the antenna itself. Now, this is a thing which we have discussed earlier, but we will again come back and discuss it. So there are three different, what it appears from the radiated power formula also, there is a reactive component which acts at the short hours or shorter distances. As the distance from the antenna grows, this reactive component goes to 0 because it is a 1 over r cube dependency. Okay, so that's what exactly is even again summarized in this particular schematic, is that from the antenna, the origin, to a particular value 0.62 square root of d cube over lambda. This is called near field reactive zone. Okay. Then from that 0.62 d cube over lambda, square root of that, to up to 2d square over lambda, this region is called Fresnel zone or radiating near field zone. So the reactive term is almost vanishing and you have a radiating zone. The third one is anything above, beyond 0.d square, 2d square over lambda is called far field radiating zone or Fraunhofer zone. Okay. So depending on these three different zones, antenna behave differently. For our case, when we are studying the power patterns, we are mostly studying them in the Fraunhofer zone. So you can see that these side lobes and everything appearing over here in the bottom right figure in the Fraunhofer zone itself. Now coming back to the same slide again, we just wanted to make a couple of points in this power pattern plot, that this distance between the half power points is called HPBW and between the two nulls is called FNBW, right? This is very important in terms of a radio telescope because it also defines the field of view. Okay, as we said earlier, that below this the sensitivity of a given telescope goes down, reduces. Also, this angular width between two half power points gives us another very important aspect towards resolution. What is resolution? We understood in the first lecture the ability of our telescope to distinguish between one star in this direction and the other star in this direction. The ability to decipher the angular separation between two stars is called resolution. So if they are very closely spaced within this half power beamwidth, this particular telescope will not be able to distinguish them between them. They will see them as a single star. But if they are apart by angular separation more than the half power beamwidth, then there is a possibility of distinguishing between these two stars. Okay, so this again, this particular component with respect to the radio astronomy point of view is very important. Now coming to the revisiting the power density. As we know, for any given setup, we have shown the example for the Hertz dipole. Now we generalize this. So for any given antenna, we first calculate the electric field, we first calculate the current density, then from there we get the magnetic vector potential, and from vector potential we get the H, or the magnetic field. From H we get E, or the electric field. Once we get the electric field and the H, we can choose the right coordinate system which describe the system at hand. Sometimes it has a spherical symmetry, sometimes it may have a cylindrical symmetry. Okay, cylindrical symmetry, for example, like for a thin wire, for example, it can have a spherical cylindrical symmetry. Now in those cases you exploit that symmetry and move from the Cartesian coordinate to that particular coordinate system and redefine your E and H in that coordinate system. After that is done, then you calculate what is called the W, or the Poynting vector. So when Poynting vector is defined, then from there you can finally calculate the power density, which is W dot ds, or the normalized normal component of the Poynting vector to the entire surface. So once that is done, you can essentially calculate the real, that goes to the real value of E cross H, and then you know the E, you know the H, so you can calculate the real value of H, E and H, and then finally you integrate and you get the W average. Now, what is radiation intensity? It is basically the power radiated from an antenna per unit solid angle. The radiation intensity is the far field parameter, and it can be obtained by simply multiplying the radiation density by the square of the distances. Okay, so we define it as U, which is R squared times the radiated power, W. So U is the radiation intensity in W per unit solid angle, and W rad is the radiation density in watt per meter square. Now for radiation intensity, we can also express that in terms of theta and phi, and that will be just R squared over 2 eta, where eta is intrinsic impedance of the medium, and E square. So if as we know, the R component of the electric field vanishes, so theta and phi component exists, and so it can be written in this format. The power pattern is also a measure of the radiation intensity, and so total power radiated by integrating the radiation intensity is obtained by integrating the radiation intensity over the entire solid angle. Okay, so for isotropic source, U0 is P rad over 4 pi. Straight again. Radiation directivity is defined as the ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all the direction. Okay, so to make it simpler, you have the radiation intensity over the isotropic radiation intensity is given by the equal to the directivity of the antenna. So as we know from the previous slide, that for an isotropic antenna, it is P rad over 4 pi is U0. So U by U0 is given by 4 pi U over P rad, where U0 is the radiation of the radiation intensity of isotropic source, and P rad is total radiated power. Okay, and U is the radiation in a particular radiation intensity in a particular direction. If the direction is not specified, it implies the direction of maximum radiation intensity. For antennas with orthogonal polarization components, we define partial directivity of an antenna for a given polarization in each direction. So Then in each direction, total directivity is sum of the partial directives in for any two orthogonal polarization. So like d naught is equal to d theta plus d phi, where d theta is given by 4 pi u theta over p rad theta plus p rad phi, and the other one is 4 pi u phi over p rad theta by p phi. These are just direct details. You don't have to worry about all these details too much for this particular course, but just for completeness, we are putting it here. So radiation intensity for all other sources, the maximum directivity will always be greater than unity, and it is a relative figure of merit which gives an indication of the directional properties of the antenna as compared with those of an isotropic source. Directivity is important, as I said. I mean, some antennas really need to be very specifically designed so that it has a maximum gain or maximum sensitivity towards a particular direction. For example, for satellite communication, where the isotropic source is the ideal thing if you really want the radiation to be in all directions, omnidirectional. Okay. So the values of directivity will be equal to or greater than 0 and equal to or less than the maximum directivity. For example, let the radiation intensity of an antenna be of the form U as given by this, where B naught is a constant. U maximum is given by, of course, this functional form maximum of that, and P rad is given by this. So if you really want to find the directivity expression as a function of theta and phi, this is given by this whole expression over here, where the top one is directional property and the bottom one is intricated property or response over all theta and phi. Directivity for the major lobe or direction of maximum radiation can also be written. For the major lobe, it can be written as for that particular beam solid angle, where theta sigma A is the beam solid angle and is given by this particular formula. Instead of using an exact expression of directivity to compute the directivity, it is often convenient to derive simpler expressions, even if they are approximate, to compute the directivity value. So essentially, for a non-symmetrical pattern, directivity can be approximated to d naught is equal to 4 pi over sigma A, where the beam solid angle, and if you have a directive along beam width along x and y, that also can be written. So then d naught becomes equal to these values. The next parameter we are discussing today is the antenna efficiency. Now we know that any real antenna cannot be completely lossless. Okay, there will be losses due to several reasons. I mean, the design may not be exactly matching with the radiation wavelength. There can be losses between the mismatch of impedances in the transmission line and the antenna. There are ohmic losses also. Okay, so overall the entire antenna inefficiencies can be combined and can be written in terms of this E naught. Okay, the antenna efficiency can be in terms of ER, EC and ED, where E sub R is the reflection efficiency, E sub C is the conduction efficiency, and E sub D is the dielectric efficiency. Okay. If I put in the value of something called a voltage reflection, this is something completely different. If you already know it, it's fine. Just these are the if the any network, any electrical system can be defined in terms of a two-port network. In that, there is, of course, the characterization happens in terms of the input and output impedances. So in that case, there is a reflection where one component ends, another component begins, and this reflection coefficient is measured in terms of the antenna input impedance and the characteristic impedance of the transmission line. You know, when the transmission line ends and the antenna begins, there can be a junction where there may be an impedance mismatch, for which the amount of voltages which was flowing into the transmission line may not be efficiently 100% converted into radiated power because of the impedance mismatch. Some of the incoming current can be reflected back, and those are standard things. You don't have to worry too much about this because this is just for completeness over here. This won't be part of your assignments and other things. Gain and realized gain. So of course this is a system, it is radiating power, it is receiving power in the reception mode, and so there should be a gain involved. Okay, now what the gain looks like, of course it looks like similar to what directivity is. So radiation intensity over total input accepted power. Okay, that the ratio of this is called the gain. Okay, in most cases we deal with relative gain, which is defined as a ratio of the power gain in a given direction to the power gain of a reference antenna in its reference direction. Okay, so G is given by 4 pi U, the radiation intensity, over the input power for a lossless isotropic source. If you rewrite this, so the gain or the relative gain can be written in terms of the efficiency of the antenna, radiation efficiency times the 4 pi over U theta phi over P radiation, or that is the directivity. So directivity and gain are almost proportional, and multiplicative term is the efficiency. Another term is called beam efficiency. This is the ratio of the power transmitted or received within a cone angle of theta 1 divided by the power transmitted or received by the antenna totally. Okay, so that causes the beam efficiency along a particular direction or throughout the main major lobe or primary lobe. Bandwidth, it is defined as the range of frequency within which the performance of the antenna is sensitive with respect to some characteristics conforms to a specific standard. The bandwidth is the range of frequency on either side of the central frequency where the antenna characteristics like input impedance, pattern, power pattern, beam width, polarization, etc. are within an acceptable value. So we cannot design an antenna which is monochromatic, means it only operates in a single wavelength. Whenever we do some radiating antenna, there will be a range of frequencies over which it is sensitive to. So this range of frequency where the important antenna characteristics like the efficiency, the primary beam pattern, radiation pattern, the antenna impedances, polarization, etc. characteristics are within a desired value, that bandwidth is called, that frequency range is equal to the bandwidth of the antenna. Okay. So that brings us to the close of this particular lecture. Of course, we have taken a lot of material from different books, particularly for the antenna theory. We have taken it from Balanis, the book of Balanis and book of Krauss. Fantastic textbooks. If you want, you can please go ahead and pick them up and read it at your own time. Thanks for joining us. See you in the next lecture. Thank you very much.